Good morning. This is going to be the review for the Math 170 midterm review. So we're just going to move over and start working through the 40 questions. We may break this up into more than one video as need be, but hopefully you've already worked through the practice, the review test. I have changed a few settings, so please go ahead and take a look at things. The best way to prepare for the midterm, as I've been told by students, as I've taught this class many times, is to work through the midterm review until you get 100%, and then maybe do it some more. But practice it, work through it. Those are the types of questions that are on the midterm was created with the same, from the same question banks and the same settings. Okay, so we're going to get going on this. You have until, anyway, watch for the announcements on the exam. So let's see, what do I do here? Let me switch over. So here's our first question. And it's asking whether this listing of points represents a function. And again, to determine a function, what we look for is that each input has one output. So we look at the inputs, all the x values, and it turns out they're all different. So they are guaranteed, since each input is different, they each have their own output. Okay, so we can mark that one as yes, this is a function. The domain, it is the listing of the x values, the input values, so -8, -4, 7, and 8. -8, -4, 7, and 8. So that's that one right there. The range is going to be the listing of the y values, -3, 8, 7, and we don't have to list the 8 a second time, so we're just looking for the 3. -8, -3, 8, and 7. -3, 8, and 7. There we go. So just the y values. There we go. On to the next. So determine whether the following equation defines y as a function of x. First of all, we're looking at the x. We actually look for the y. We need a singular y. We need something that's not y squared. The reason y squared is not a function is because for a given x value there could be two. When you square, you get a positive or a negative. So -3 is equal to 9 and +3 is equal to 9. So anyway, if y is squared or you have absolute value on y, it's not going to be a function. X can basically be anything it wants, and we're focusing with this question on the y. Okay. So now we're asked to evaluate this function at the given values of the independent variables. Simplify. So we're plugging in -2, we're plugging in 23, and we're plugging in x minus 2. So we could do each of these separately, and you're welcome to use a calculator, but at the same time we'll do these writing them out here. Okay, so we get the square root. We're putting the -2 in for the r. So that's what we're plugging in for. So really this function, what you want to look at it, it's the square root of some input plus 2 minus 7. Okay, plus 2 minus 7. Well, -2 plus 2 is 0. Square root of 0 minus 7. Oh, that's just minus 7. So we can put that one in there. And again, you'll have different, your questions will be a little different. That's okay. How about 23? So we kind of see how this is going. We can put in the square root. 23 plus 2, that's going to be 25. Square root of 25 is 5. So it's 5 minus 7. We should get a -2. go. Now this one, we're not going to get a numeric answer because our input includes a variable. And this is where it is important to have this set up with the open parentheses. Whatever is in this parentheses, that's what goes in there. So x minus 2 is going to go into the open parentheses. And again, you get a negative, you take off the parentheses, there's nothing to distribute or anything, so you get a negative 2 plus 2, that's 0, so you get the square root of x minus 7. We can use this square root of x, use the right arrow to step outside, and make sure your minus 7 is outside of the radical, and let's check our answer. We're good to go. Let's keep moving. And incidentally, if you don't have questions on some of these, fast forward, scan forward, whatever you need to do. Okay. Use the graph of A to determine the function's domain, B, the function's range, and C, the x-intercepts, if any, the D, y-intercepts, so all this stuff to figure out. So the domain, we see that this function starts at x equals 0 and it goes forever. Okay, so 0 is included. That is a, let's see if they give us all this stuff. That's a square bracket. They don't really give us the brackets, so our computers, we use this bracket. We're going to go from 0, but we do need the infinity, okay, because it never stops. Infinity always has a parentheses, never a bracket, because the idea is we never get to infinity. The range, so the highest y value is negative 2, and then this is going downward towards negative infinity. Now when you list either a domain or a range, you always list them from the smallest to the largest values. The smallest value actually is going to be negative infinity. It's coming down here. So we're going to list going from, we're going to go from negative infinity, again, which always has a parentheses. So we put a minus infinity until the highest y value, comma, is going to be minus 2. And then that is included, so we use one of these square brackets. Okay. Determine the x-intercept. Well, the x-intercept, here's the x-axis. It never even gets up there. Let's see, why does it do that to me? It's kind of... don't want that. There are no x-intercepts, so what are we supposed to put? Oh, here it is. We check on B. You look at the answers. Okay, there is no x-intercept. Okay, so determine the y-intercept, if any. Well, we do see a y-intercept. It's clicking. It's right there on the y-axis. That is a value of 0, negative 2. But it says just type the integer. So they're just looking for the value. I guess it's right there. The y-intercept is negative 2. So type an integer. If they wanted an ordered pair, they would tell us to put an ordered pair. Okay. And then the final, what is f of 4? So to get that, we come back here. So when x is 4, 1, 2, 3, 4. Let's go with the red this time. 1, 2, 3, 4. We come down here. That's where the point is. The y value is negative 4. And remember, you can always fast forward through this because a lot of you're probably thinking faster than I can talk. But I just want to walk through each of these. We got 440. We're getting there. Main thing I just want you to understand what's going on. So that's the graph and equation of the function f are given. So we've got both the equation, the graph. We've got what our graphing window is. So use the graph to find any values of f has a relative maximum, and use the equation to calculate the relative maximum for each value. Okay, so and then do the same thing for minimums. Okay, so we can see from the graph that here's a maximum right here, a maximum, and we can see that's happening at x equals -2. And then we see a minimum over here, and that's happening at +1, right? But to find the value, I guess we could kind of see it. Does that look like 2? It could be. What is this? But you know, here's our window. Our y's are going from -27 to 27, and you got to, you know, they've got each tick equals 3, so it's actually probably going to be like -6 here. And anyway, what they want us to do is to use our graphing calculators. Sorry, I didn't have it pulled up yet, but well, okay, here it is. My little wabbit. Let's put that over. Now that the calculator's up and running, we can actually go ahead. Mine always has this in memory. We enter it in 2x raised to the 3rd plus 3x squared minus 12x. Just make sure you get it in correctly. If you make an entry error, of course everything else will be wrong. This helps us with our window, so I'm going to go to the window. The x is going from -5 until 5, and the x scale is 1. Okay, that's good. The y's, y minimum is -27, and our maximum is +27, and the scale is 3. So that allows our graph to look like their graph, because it'll have the same window. And now we just need to find this max. I'll do that first. So it's under the calc tool, second calc. We're going to find the maximum, number 4. And to do that, it asks for a left bound, so we walk our little spider dude back over the mountain, back to the other side. So I just need to be the left of the maximum. And then I go to the right bound, so I just keep walking. Now, it's not. We don't have our answer until it says it's a maximum. It's a guess. Sometimes people will put this in. Nope, that's not the answer. The answer is here. The maximum is at -2. This would round to 21. Okay, so that is actually 21. You might have been able to count it, but I don't know, not me. So we choose the function f has a relative maxima. At. So what does that mean? At is location. Location is x. We locate things by their x value. So this is -2, and the value, the relative maximum is, that's its value, that's the output value we found out was 21. Surprised this thing's supposed to stay there. Okay, oh, I put it down. That's right. Okay, so far so good. We want to find the minimum value, and we do it the same way. We go second calc, except this time be sure to ask for the minimum. If you ask for the wrong one, you get the wrong answer, right? So it wants a left bound, so somewhere over here, this is to the left of this minimum point. I'll just hit enter, and then I need to do a right bound, so I come down through the valley, and we go to the other side, anywhere along here. I just make sure I'm definitely past that minimum point, hit enter, and then enter for a guess, and it will tell me that the minimum is at, we'll call this +1, we round it to 1, negative 6. We could kind of spot that from the graph itself, but let's see. Here we go. Select the correct function. Has a relative minimum, or it doesn't have one. It does, definitely. And at is the location. Location is positive 1. Let's get this stuff out of the way. Positive 1, and as we saw on the calculator, its value is, the y value is negative 6. Okay, so it's going to get used to reading these. Let's see, I think that's it. And so we've answered everything. Let's check our answers, and we're good. Doesn't that give you some feeling of confidence when your teacher can get the answers right? I sure hope so. Determine whether the function is even, odd, or neither. Then determine the function is symmetric. Now, we'll do it both ways, but the easiest way I spot even, odd, or neither is I look at the exponents. This is a 3, and actually this is x to the first power. That's an odd number. All the exponents are odd. It is odd. Okay, it is an odd. Now, another definition is you look at the symmetries. So I'll do a quick graph of this, and we could probably leave this window as is. Again, I want to give multiple ways. If you're good with this, you can kind of fast forward through this if you like, but symmetries plus 2x. Now, odd functions need to have what I call spinor symmetry, symmetry around the origin. So if you spin it, it's going through the origin usually. It doesn't have to, but if you spin it around the origin 180 degrees, it lands on itself. That's the kind of symmetry we're looking for. And here it comes up and goes, and yes, if we spin this thing 180 degrees, you know, it's halfway around, it will land back on itself, so it's definitely odd symmetry. But you can also tell from the exponents. Had we had an x squared in here, it would have neither. If you get a mix of even and odd exponents, it's neither. And had it been like a plus 2, let me just kind of, because you don't know what you're going to get, you might get this one. If we had a constant on here, say like plus 2, whatever, plus 5, anything. This is really x to the 0 power, 2x to 0. So if you've got a number here, that's and a 0 is an even power, so this would be a neither. Okay, so just watch for it. It's all odd exponents now, but if there's a constant out here, just a number by itself, that's really got an invisible x to the 0, that's an even. Okay, so we'll take that off. It's not part of this question, but it might be part of yours, so I want you to be able to get these correct regardless of what version you end up with. Determine whether the graph of the function is symmetrical with respect to the y-axis, the origin, or neither. So I guess that was good. We saw that it's the origin. So if it is odd, it will always be origin symmetry. If it's even, it will have y-axis symmetry. And if it's neither, if it is neither even or odd, it will not have either of those symmetries. It's kind of a connection. You get both. 2-for-1 deal. Okay, so we're good. Let's see, where are we? We're only to 6 so far. We'll just keep plugging away. Evaluate the piecewise function at the given values of the independent variables. So we've got these different values. With a piecewise function, one of the first things you do is you determine which piece you get to use for which input. Okay, so when we have an input of 3, we look over here. This is sort of our domain section. If x is not 2, then we use this one up here. If x is actually 2, then we use this one here. Well, x is not 2, it's 3. So we're going to use this piece here. Okay, and so again, we plug in 3 for each of the x's. 3 squared minus 4 over 3 minus 2. That's 9 minus 4 over 1. That's kind of helpful. And so that's 5. That's our answer there. our 0, again, 0 is not equal to 2, so we use the top part. We put in 0 for each of the x's, 0, 0, so you get negative 4 over negative 2, which is positive 2, right? And again, and then finally, we've got h of 2, and 2 is equal to 2, right? So we are going to use this x equals, we're going to use this as our value, as our function. Now, there's no place to plug anything in, right? Because it's just 3. Let me do this. This function is just y equals 3. The output is 3. There's no x here. If you want, it's x to the 0, but so they're just giving us a value. Okay, so we'll go ahead and check that answer, and it's correct. Okay, so piecewise functions always check which piece you use first, and then you only use one piece for each input. That's what makes it a function. 8. The difference quotient. Okay. So they just want us to plug all of this in. Again, this is setting us up for calculus. So let's go ahead and do this one. You'll see why you're doing all this right now. It's really a slope formula, but so we're going to need this part, and then we just subtract the function as it is. So I'm going to, so what this means, remember, is we're going to rewrite this function, and everywhere there's an x, we'll put a nice big open parenthesis. So it's 2 parentheses squared, 2x squared plus x plus 2. But in writing it this way, just makes it so much easier. Whatever's in this parentheses needs to be inside these parentheses. X plus h, x plus h. Now they do want it simplified, so we got some work here to simplify this. And then again, what we're going to do is in the numerator, we're going to be subtracting f of x. So we need to FOIL this out. So this is x plus h times x plus h. And using FOIL, you get x squared plus xh, or hx. And then we get, so that was that one, and that one. And then we get h times x again, so that's going to give us an hx. And then we get h times h, which is h squared. Middle terms combine into 2hx, so this whole thing becomes, and then we multiply everything by 2. Okay, so let me, right, because there's this 2 on the outside. That's just this part. So I'm going to distribute that 2, and we get 2x squared. This is hx and hx, so there's 2hx times 2, so that's going to be a plus 4hx, and then plus 2h squared. So that's just that first term here. Next term, nothing really to do, right? There's nothing to distribute, so that's just going to be, take off the parentheses, plus x plus h. No like terms with that, and then plus 2. So I think that's pretty much it. What we do is now we're going to do the second part. We're going to subtract f of x. Now be careful here. You want to subtract, and you put a parenthesis around it, the original function. F of x is 2x squared plus x plus 2. Okay, so this negative is going to distribute through. So I'm just going to, I don't want to have to write too many different things. But this is going to be negative, this is going to be negative, and this is going to be negative. And you have to distribute. A negative 2x and a positive 2x. Those little babies go away. We have a negative x and a positive x. Those cancel each other out, become zeros. And we have a plus 2 and a minus 2. Those go away. Okay, so I've kind of simplified. Now remember, we have all of this is over h, so whatever's left, which we have 4hx, we've got plus 2h squared, and then we've got plus an h. Right, that's that. Now we're not done yet. In the numerator, an h can be factored out, and then we'll be able to cancel the numerator with the denominator, the h. Okay, so factor out an h. Take out the h, you've got 4x. Take out one of the h's, you've got plus 2h. And then on the end, you take out the h. What's left is a 1 plus 1. Okay. And the best way to check is if you distribute it back through, you need to get to where you started. 4hx, 2h squared, plus h. Okay. Let's just change color one more time. So when we cancel, this h divided by h is 1. So there's our answer right there. As simplified as we can get it. We can read that. 4x plus 2h plus 1. And what you do in calculus, this is we use this to take something called a derivative. We let h go to 0, so that kind of disappears. You'll see the derivative is 4x plus 1. Just to give you an insight to where we're taking all of this. This is why we do this, so it gives us a rate of change. And that's the beauty of calculus, is it gives us a mathematics of change. And that's our lives. Everything is change. The only thing that doesn't change is change. I don't know if that makes any sense, but it sort of does. We always have change. That's not going to change. Okay, but we are resilient people, and we keep moving forward. So we've got 8 out of 40. Let me get to 10, and I'll maybe take a little break. You're probably doing fine, but I need to stretch a little bit. So use transformations of x squared to graph the following function. Now, again, you can do it multiple ways, but what we want to remember, maybe the quickest way, is what does an x squared look like? Well, an x squared is going to be a u-shape, and it's going to be u-shaped up. So what are we doing with this transformation? Well, we're adding 4. Now remember, that's inside the function. It's happening inside this x squared, so that moves it actually in the negative direction 4. So this is going to move over this way 4. And then we're adding 3 on the outside. On the outside, the movements are what you think. So adding 3 actually does move it up 3. So notice this would be 0, 0. So we're going to have this going upwards to the left 4 and up 3. So let's see how this tool works. And that's the other reason I like doing these is, so we got this little, this guy, and we know that parabola, I guess to use a technical term, we come over 4, so we start at 0, 0, 1, 2, 3, 4, and then we go up 3, 1, 2, 3. Let's see. Oops, oh, I guess I have to do that. Can I move it? Oh, this is how it works. So we do a vertical shift. Let's see. Let's go -4. And then, oh, that's vertical. Horizontal. See, I'm dyslexic. I mix these things up. We want to go +3 for our vertical. The horizontal, we want that to go in the negative direction, I think. Now someone was telling me that they had problems with this, and let's see. No, I don't want to reflect it. There, oh, that's why, because I clicked on that. So -4 does move it in that direction. I didn't hear back, so hopefully that it all worked out. Let's save it, and let's check our answer. Yeah, it liked it. Okay, so that, again, even if you know how to do it. Now again, you could also graph this. You've got a graphing calculator. That's, you can use it. If you weren't sure what to do, just come here, graph it as is, x plus 4. And this is a good thing to do even if you're kind of feel like you know what you're doing, because I always feel like I know what I'm doing, but I end up sometimes making some mistakes. It happens. It's kind of a let me go for a zoom standard. Gets us back to that's kind of what this is. And yeah, I'm in the right place. I didn't move it the wrong way, so it's worth doing a check. I recommend use a graphing calculator. Check it out. Let's clear this. Let's get one more, and we'll just keep moving. I'm not sure how much time we've spent so far. Begin by graphing the absolute value function f of x equals absolute value of x, then use the transformations of this graph to do this. I'm going to show you how you can actually graph this as well, but let's do this one like the other, because it looks like we're not actually graphing it, but we are saying what's happening to it. So again, what does an absolute value function look like? It's a V shape because it comes here and the V is at 0, 0. So that's, it's going to be a V shape. So what's going to happen? We start from inside the function. It's going to get moved to the left 5, right? Because it goes in the opposite direction. Left 5. As we come out, I guess, following an order of operations, once we're outside, it gets multiplied by a -3. So that's happening on the outside. A negative on the outside affects the y values, and so it's going to flip it over the x. Okay, reflect, flip, reflect over x, and this 3, since it's on the outside, it's going to stretch by 3. And since it's on the outside, what stretch? It's a vertical stretch. And then finally, we've got this -4, so it moves down 4. All this stuff's going to happen. Down 4. Okay, so let's see what happens. Let's go answer these questions. What transformations are needed in order to obtain the graph of g of x from this? Select all that apply. So you're going to need to do a horizontal stretch. No, vertical stretch. Vertical shift. Certainly a vertical shift. That's what these are. The 4 is a move down. That's a shift. You do a vertical stretch or shrink, but vertically we're stretching it by 3. We are reflecting it over the x-axis. That's because there's this negative on the outside. Remember, the negative affects the y, but as the y changes, you get the y, positive y's become negative y's become positive y's. That's a flip over the x-axis. Okay, so just got to think. We're also doing a horizontal shift. We're going left or right here. Wow, a lot of stuff. We do not reflect it over the y. That would have to be a negative coming inside here somehow. And then now we can select our graph. Again, we're going to graph it just to be sure, but let's see if we can follow this. We flip it over the x, so it was going up, so it should be going down, which they all are. We know it moved to the left 5, so these guys, B and C, went to the wrong direction, so it's either A or D. Kind of hard to tell the difference. We go over 5 and then down 4. One's maybe more stretched. Wow, they're making it hard to determine. Let's bring it up. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's compare it to this one over here. I think, but I don't. It doesn't look like it's stretched. Let's see here. 1, 2, 3, 4. Oh, okay. But okay, this only went over 4, and then it goes down 5. 1, 2, 3, 4, 5. So if you got them reversed, as far as your shifts, this you'd choose A, but we're not going to get. We're going to go with B or D, okay, because it went over 5 and down 4. That's the correct one. Now, before I do this, I'm going to go ahead and graph this, and I'll show you how you can graph an absolute value. So we just put in the -3. We need the absolute values, and where you find it on the TI-84, 83 is you go to Math, over to Number, it's been a while, and ABS, that's your absolute value. Notice on you may either have ABS with a parentheses if you've got the older operating system, or you get this, which actually looks like a absolute value, right? And then we just put our x plus 5, and then we subtract 4. And then again, we've already done the thing, and so yeah, here it is, and we see over 5, down 4. Hopefully you can 1, 2, 3, 4, 5, and then down only 4. Okay, so we feel pretty good about the one we chose, hopefully. And we're good. Okay. All right, 10 out of 40. Hey, I got a second win. I'm just going to keep going. It's a little easier for me to just keep making. Maybe I'll do another 20 before I take a break and get myself some more coffee. But let's just keep moving. And then again, you fast forward to what you need. Watch this at double speed, whatever you need to do. But I just want to make sure I got it all for you. Use this graph to determine open intervals on which the function is increasing, if any, which it's decreasing, and open intervals which it's constant. So we always read from left to right. That's the important thing, because if we don't have an orientation, this line here could, again, depending, if, we could look at it as increasing or decreasing, but when we think about increasing, decreasing mathematically, we are always reading from left to right. So x is always increasing. The answers on this about increasing, decreasing, or constant is what is happening to the y value, the output, as x increases. X is always going to be increasing. And again, I read left to right, right to left. Took Arabic for a year because of that, and picked it up quite quickly. I can read upside down, and that all these things are great, but they mess me up in math because I tend to read graphs any direction I want to read it in. But for these answers, we've got to read it from left to right. So this is definitely going left to right. We're going down here. This part is decreasing. So it's going to decrease. Well, where's it increasing? Okay, so this is how we have to answer it. So that we're decreasing, and then this is what we call constant. It doesn't change. It's horizontal. There is no increasing. No increasing on this graph. No increasing allowed. Okay. Second question. Function is decreasing on what intervals? Now this, we got some increasing or decreasing stuff. And again, where we're coming from is negative infinity. And again, when we report this, we're reporting the x values, not the y's. It's weird. We're looking at when the y's are decreasing, but we report the x. And it keeps decreasing until it gets to 1. Now, at 1 itself, it's actually neither increasing or decreasing because it's just at a point. So that's why we use it as an open interval. Do not use, when you see open intervals, do not use brackets. Use parentheses. So we go parentheses, not parentheses, negative infinity, comma, all the way to 1, and then we close the parentheses. Okay, that's good. And then where's it constant? Well, it's constant everywhere else, starting at 1 all the way to infinity, positive infinity. So we see a constant section. And again, you'll get something maybe a little different, so you got to be prepared for all of these. So this one, again, going from smallest to largest, we report that at x equals 1. Again, on one side it's decrease, on the other, but at 1 it's neither increasing or decreasing until, and then we're constant now until we get to infinity. There we go. Let's clear this off. think we got everything answered. Yeah, so not increasing. Here's the decreasing part, and here's the constant part, and we did good. 11 out of 40. Let's keep moving. Try to speed it up a little bit if you need, or maybe I'm doing fine. We'll see. So we're given two functions, f of x, a g of x. We want to find the following. So we want to find the fog, as they say, f composite g, or g composite f. These are two different things. And then we've got some values to plug in. Okay, so we're going to do the first, f composite g. Now the way we look at this is whatever the x is closest to, that's going to be sort of the inside of the function. That gets what plugged in. The furthest apart is the outside function. We can also rewrite it as f of g of x. So you kind of see that this is it's kind of like the f function is eating the g function, and so the f is outside. So we take our f function for x, and remember, just make a big old parentheses, because that's where we're going to plug something, minus 3. So this is our function setup for x minus 3. And we just change our format. Instead of using an x, we use a big parentheses. Different symbol, but actually much more helpful. And what goes in that? Well, g goes in that. G beaver. I don't know. You leave it to beaver. I grew up on that stuff. Child of the 60s. Actually, little child of the 60s. A teenager of the 70s. Young adult of the 80s. And old man of the of the current time. But I'll tell you what, I kind of like being old now. It's what I've always wanted. It's because I figured out a lot more things. I was a very gullible kid. So, and they want it simplified. Okay, we'll do that. I don't like to simplify because it's, you see, when you leave it this way, you see the outside function and the inside function. Now that we go to simplify, we lose the evidence of where things came from. But we'll do it because that's what they asked, right? Distribute the 4, we get 12x squared. Oops. Wow, I didn't know I could do that. That's good. Now I know. I just click on a button and I got an eraser. 12x squared, it's minus 8, minus 3. So negative and negative, when you're adding, they actually go together. They're going in the negative direction. It says negative 11. Okay, I'm going to write that here. So our final answer, we put in 12x squared, little caret thing, and then you arrow to get down, and then we just do minus 11. Now this will actually maybe make our calculation easier when we go to plug in the values, but anyway, that's it. Now, G composite F, so the B part, we're going to switch gears here a little bit. Oops. Come on. I don't want that yet. Okay, sorry about this, folks. Good. Okay. Okay. Okay, that's how I do it. So now we want G of f of x. So now the outside function is the g function. So we take our g function here, and we're going to rewrite it as 3 big parentheses, that's x squared, 3x squared minus 2. what do we put in there? Well, we put the whole f function, f of x, or 4x minus 3. That's what goes in there. Oh man, now we got to, because they want us to simplify it, we got to FOIL this thing out, right? So we got to square this thing and then distribute the 3 and then subtract the 2. So this is a little more complicated, but we can handle it. 4x minus 3 times 4x minus 3. Okay, distributing 4x times 4x is 16x squared. 4x times negative 3 is going to be negative 12x. Negative 3 times 4x is negative 12x. And then we get negative 3 times negative 3 is going to be a plus 9. So in the middle we get a minus 24x. 12, negative 12, negative 12. We got our 16x squared. I need to get a new tablet. Sometimes my 2's don't get there. And then we still got this 3 on the outside, and we got the minus 2 on the back side. So we just kind of did this part. Distribute the 3, and then we can subtract the 2. So 3 times 16 is 3 times 6 is 18. Carry the 1. That's 3. That's 48 x squared. And 3 times 4 is 12. Carry the 1. 3 times 2 is 6. Plus 1 is 72. X, and then 3 times 9 is 27. We subtract the 2, so that's going to make that to 25. I'll just save myself instead of rewriting all of this. And notice there's a little square there, supposed to be. So that's our answer here for the B part. Let's see if I can read that. 48x squared. Is that plus 72? It's minus 72. Minus 72x, and then plus 25. Get that stuff all out of the way. And then f of g of 1, so we come back up here. So the simplifying part is kind of cool, because now we just plug in 1 for x. 1 squared is 1. 1 times 12 is 12. 12 minus 11 is 1. Okay, so we can do that part. And actually, all that grumbling, we plug in 1 for x into our g of x, g of our g composite f of x. So we get 48 minus 72 plus 25. Gonna need a little bit of help with that one. Probably writing down will be good. So we get 48. So I like to do is take the positives, 48 plus 25, and that's going to give us 60, 73. And then we subtract our 72. All right, plugging in 1 for each of these. Hey, we also get 1. That's kind of cool. That's kind of cool. Oops, what happened there? I don't want that. Okay, put a 1 in there. We checked our answer. We're good. Okay, hopefully that's clear. And again, well, just keep moving. I'm not really trying to completely teach these sections, but reviewing how to do them, but hopefully it makes some sense for those. Again, now we've got a F composite G, so again we're going to do the same thing, but then they're going to want to know about the domain of F composite G. And with that, we have to check the domain of the input, and then we also have to check the resultant domain of the final output function. Okay, so I'll show you what that means. I guess we use, so we're doing F of composite G. So we're going to take our f function, so that's f of g of x. We're going to take our f function, and everywhere we see an x, we're going to put a big parenthesis. So there's a parenthesis there divided by x plus 1. So just big parentheses. What goes in that parentheses? Well, g goes in that parentheses, g of x. And what is g of x? It's 6 over x. 6 over x, 6 over x. Okay. They want the answer simplified. And what we do to simplify these, because we've got a complex fraction, we've got a fraction over a fraction over a fraction, too much stuff going on. So what we do is we're going to multiply by x over x, which is 1, because x divided by x is 1, right? X divided by x equals 1. That's, I mean, anything divided by itself is 1. So we're going to multiply by x, but we're kind of going to do it as like x over 1, x over 1. That's the same thing. And what happens in the numerator, the x's cancel, and we just end up with 6. Now notice this is, what we have is just in a different form. This we have to distribute to both of these, so the x's are going to cancel, so we get 6, and then x times 1. So this complex fraction really simplifies down to just 6 over 6 plus x. That's what it's going to be a lot easier to work with. Okay. So that's our function, and then we'll come back, we'll talk about the domain once we get this entered in. Use our fraction thing, template. Let's see, here we go. Come on, get down there. There we are. 6 plus x. Okay. I suppose I should check to make sure this all works. Sometimes I do all this recording, and after an hour of answering everything, I found out I made a mistake, but we'll check it later. And I thank you all for sticking with me through this. So what's the domain? Well, we can see at the end, if the domain questions are about, with rational functions, we can't divide by 0. That's something mathematically we can't do. If we do it, we get infinity, but that's not a number, so that's considered undefined. So yes, we can, but no, we can't. Okay, the rules, right? So we have to take anything out of the denominator. Let's see, which one are we using? So we take our denominator and we say, what would make it equal to 0? Then we can have everything in our domain except that. And so we subtract 6, and you probably could see this, but if x is negative 6, we have division by 0. Okay. And so it's going to be everything except negative 6. However, we also have to look for the very first input. Notice we had 6 over x, and even though it simplifies, where the value of x that gets plugged in first goes into it goes into the g first. So we also have to look at the input function, and that tells us that if x were equal to 0, we'd get undefined right away. Now, the end result we could put it in, but again, it passes through the g, so we need to remove both 0 and negative 6. So the way we do that is we say, okay, the domain is going to be everything from negative infinity until we get to negative 6, because negative 6 is the smaller of the two. We put a parentheses which takes the negative 6 out. We put a little union guy, means we're connecting these, and then negative 6. So this is a way we remove negative 6. Negative 6 is not included. Everything else is. From negative 6, we can go all the way to 0, but then we need to stop and take the 0 out. And we do that by putting this parenthesis saying not including 0 on this side, not including 0 on that side. But once we get past, once we get past the 0, we can keep going to infinity. So that's the way it's supposed to look using interval notation. So let's see if we can put all of that in. Oops, sorry about that. Fortunately, I remember it's 0 and -6. So let's we go parentheses, negative infinity, comma. We can go to -6 parentheses. Then we need this union symbol. So U. We put -6 again. Parentheses -6, so that's removing the 6. We go all the way to 0, we remove the 0, and we remove it completely by saying we remove both the left and right side, but then we go to infinity. Okay? And close it off by a parentheses. So watch your formattings. Yes, we can review this, but the system, it's always so nice if you get put in the way the system likes it. You get your answers, you get your test score correct the first time. That's that. Okay. More composition of functions again, and now they're using this other notation. So just to tie it all together, yeah, this is F composite G is the other way to write it. I like the way they have it here, and this would be G composite F. Okay, so again, we're going to take, with the A part, we're going to take F as our outside function. So we're going to go F of input equals 9 over X with our different symbol minus 8. What goes in here? Well, G goes in there. G of X. Right? G of X goes in there. What is G of X? It's 9 over X plus 8. Okay. And why we're doing this is to see, so we're going to simplify, because the thing is, we're checking to see if they're inverses. What makes them an inverse, notice we start at X. If we end at X, then they're inverses, because we do something and then we undo it. That's what an inverse does. An inverse undoes what the first thing did. So if we end up back at X, then it's an inverse. If we end up at anything else, it's not an inverse. Okay. So we can remove these parentheses, and we've got a plus 8 minus 8. So that gives us 9. And notice we're not trying to get rid of this X in the denominator just yet, because we don't really need to simplify. And again, if we get stuck on something where it's not X, we go, so this is 9 divided by 9 over X. So I'm going to rewrite this as 9 divided by 9 over X. And how do we do that? We flip the second and multiply. So this is 9 times X over 9. Make sure I get that. So the 9's cancel. This is equal to 9 divided by 9 is 1. This is just equal to X. So that's good. So far it's looking good, but it's got to work the other way as well. It's got to work in both directions. It's possible for it to work, to get X in one way but not the other. Those are fairly rare, but it happens. Let's see. Let's switch. Let's do the red first, and then so we're going to do G. So we rewrite our function G of X, and that's going to be 9 over something, 9 over X plus 8 afterwards, and then what do? We plug in the other function. We're plugging f of x into here. Well, what's f of x? That's 9 over x minus 8. Okay, so we've got this complex fraction first. Let's take care of that. 9 And I'm just going to go to one step. I'm going to make it multiplied by the reciprocal. So 9 times x minus 8 over 9 plus 8. The 9 divided by 9 is 1. So I've got x minus 8 plus 8. Now I'll just rewrite it because it looks like it's in a fraction, but notice the fraction's really gone. So this is just x minus 8 plus 8. Negative 8 plus 8 is 0. So that's x as well. So we did end up with both of these starting at x, both of these ending at x. We got inverses. They're inverses of each other. They undo each other. So f and g are inverses of each other. That's true. Now, even if they were like negative x, no. 2x, no. It's just got to be just x. Started at x, you got to end at x. That's what makes them inverses. And you know, sometimes the more I talk, I get back to my old accents. My family's traveled a lot. We lived down in New Orleans and Florida for when I was a kid. I was born in Seattle, lived on the West Coast a while. I've been down here for, I don't know, 16 years now. And my family's from North Dakota, so I pick up some of their accents. Anyway, it's interesting. We are from so many different places, and we fall back into different habits. So we're given a function, and now we want to find its inverse. So that's f to the minus 1. We want to find the inverse function, and we'll show you how you do that. Then we're going to graph it, and then we'll talk about its domain. Okay. So to find an inverse, what we do is we rewrite this sort of as y equals x cubed minus 1. To really just get the inverse, it's just a process of switching the x and the y. That's, you know, the x and the y switch places. So the y becomes an x, and the x becomes a y. Y cubed minus 1. Now to get it as f inverse, what we do now, we need to solve for y. Okay, so we will take this and add 1 to both sides. Doing algebra. Okay, so we get x plus 1 equals y cubed. And the way we undo a cube is we use a cube root. And we do that to both sides. So take the cube root, or 1/3 power. It's the same thing. But so on the y side, the cube root of y cubed is just y. And since it's an odd power, it does nothing to the, I mean, we're all good. If it was a squared, we end up with something that, again, we talked about that it wouldn't be a function, but cube root x plus 1. Because it's a cube root, you can have negatives in here. Square roots we can't, so that's when you would say, okay, this inside cannot be negative. But cube roots we can take because you're doing 3 and you can't get negatives. Okay, so let's go ahead and write this up for our function, and let's see if they've got, so we want this one, the cube root, and then we can put the 3 there for the cube root and x plus 1. I guess I have to arrow in here, x plus 1. There we go. So that's the first part. Now the graph, well, let's just go ahead and graph them both, right? So let's do what they say. So the first, let's clear this. We could have x cubed minus 1. Oops, careful. Got to arrow out of that, minus 1. And then we'll graph the cube root. And to get a cube root, you could go to this math key, and they've got a cube root here. Here, cube root. And they've also got any other root if you need it. do that, and we'll do x plus 1. Now, if you've got a color system, oops, it works great. Let's see what, I might have a problem with this. There we go. So what I'm going to do is I'm going to come over here. So note I've arrowed over to this side, and I'm going to hit enter, and it's going to make this one a thicker line, just so I can see what's going on, so I can see the difference between the two. I'm going to go zoom 6. That gives me my standard window. Here's the first one, and here's the other one. So they kind of, yeah, that's what an inverse is supposed to be, a reflection over the line y equals x equals y. Okay, so this 45-degree, they just kind of flip over. So that's what it should be looking like. Let's put this down, kind of freeze that in your mind. Let's see if we can pick that out. Yeah, sort of, but I think it certainly was not one of this or this. It's either, they make it so close. 2, 2. Let's see, what's the difference here? What's the difference? Oh, I see. Now notice we could look a little closer. So this is an x cubed that's been moved down 1. So it's just, instead of going through 0, 0, it's going down through -1. So it's got to be this one here. This one, it moved it to the right one. So they're kind of testing you a little bit on your transformations as well. But you could also just look here. Okay, compare a little closer. It just went down 1. Okay, so they always do this. The ones that look the closest are probably, one of them's right, one of them's wrong. So you could kind of skip B and C because they don't look alike. A and B, D are very close. One of them's right, one of them's wrong. D is the right one. Yeah. Okay. State the domain and range of f and f minus 1. Well, first function has no problems. There's no division by 0 if there's no square roots. So the domain of f itself is all real numbers. And you can kind of see that from the graph itself, right? The domain there's nothing hidden here. There's no undefined portions. The other thing is the range is also going from negative infinity to positive infinity, the y values in both cases. So the domain and ranges really are equal to each other. So the domain of f is equal to the range of the inverse, which happens to be everything. So this one's just going to be negative infinity until positive infinity. And that's going to be the same thing for the range of f and the domain of f inverse. It'd be nice if we could just click on a button, right? That said negative infinity to positive infinity, but I guess I could use this one, and then, but anyway, I don't know. However you want to do it, I kind of manually. They do have a few things that are a little easier. Let's see, and I think that we've got all our answers in there. This is 15. I think I'm going to take a little break, mostly so I could get this posted as well. So I'm going to post this part now, so some of you can start while I get on to the next. What, 25? Only 25 problems. Okay, thank you very much.